Hello. In this video we will continue our discussion of potential energy and turn to a new type of potential, the potential energy of springs. The spring force can also cause potential energy to be stored in an object's location. After all, imagine we have an object pressed up against the spring like this, contracting it. The object may not be currently moving, but as soon as we let it go, it will shoot out and go flying. Where did the energy come from to get it to move like that? The answer is that, because of the spring force, there is potential energy associated with the object's original position. We were able to work out together what the potential of gravity is by calculating the work required to move an object vertically and the work done by gravity when an object falls. However, because the spring force changes at different positions, calculating the work done by a spring is a bit more tricky and requires calculus to do. Therefore, I'm just going to give you the equation. U of a spring equals half times k times delta x squared. Recall that k is the spring constant, which depends on the spring involved. Delta x can also be written as this, where x is the position of the object and L is the rest length of the spring. It is just a measurement of how compressed or stretched the spring is. You should also note that this potential is only relevant if the object is in contact with the spring, or attached to it. If there just happens to be a spring 100 meters away, but the object is not attached, then there won't be any spring potential, since there isn't any spring force. Let's look at this example here, where the ball is pressed up against the spring. It is contracted in such a way that the spring is 20 centimeters shorter than its rest length. What will be the ball's kinetic energy as it leaves the spring? Well, the work done by the spring potential is negative times the change in spring potential. Initially, the spring potential is at 1/2 times k times delta x squared. In this case, delta x is 20 cm and k is 200 newtons per meter. If we work out the arithmetic, we get 4 joules. Once the ball leaves the spring, the potential energy is 0. So if we plug things into this formula here, we will get 4 joules. This work done by the spring equals the difference in kinetic energy of the ball. So the ball goes from 0 joules of kinetic to 4 joules of kinetic. So 4 joules is the answer. And that is really all there is to know about spring potential energy. Now I just want to say a few words about potential energy in general. Potential energy only depends on the position of the object, and not on how it got there. For instance, an object could just rise straight up and have a certain gravitational potential, or it could take some crazy path all over the place. But if they both end up in the same place, then the potential is the same. We call this path independence, and it simply means that whatever path we take to get to a position, the potential is the same. This path independence is what makes some forces have a potential energy associated with them, whereas other forces, like friction, do not. See, for friction, the way that you get from point A to point B matters a lot. For instance, if I slide along the surface here, then I will experience a good bit of friction. But if I instead jump from point A to point B, I haven't experienced any friction at all. For that reason, friction cannot have a potential associated with it, since the path we take affects the amount of friction that we feel. Okay, that's it for this video.